This is our last block for lecture 10, and I'm going to talk a more complex models to do binary and multinomial classification. Okay, so I'm going to introduce you to nonlinear classifiers and also to decision trees. Okay? Same references. Okay? So when y is a binary random variable, we model the probability of y equals to 1 given s as a nonlinear function with a linear argument. Okay, so the argument of this function is x beta. So we have the probit, we have the logit, and if y takes values on like multiple choices, we have the multinomial logit. And what's common in all these models, you see that the argument is always linear. Okay, and what these models are doing, they try to linearly separate classes on the covariate space, so that we see that the classes are linearly separable. Okay, so this is very important. Okay? So as we see here, we can perfect split in model the two classes, because two classes 0 and 1 are perfectly separable by a linear model, a linear frontier, okay, between the two. So there, however, in most situations, especially if we move to high dimensions, the classes are not linearly separable on the feature space. Okay, so we need to use a more complex model. So instead of just looking at g of x beta, we are going to look at g of a nonlinear function f of x indexed by a parameter vector theta. Okay, and what are the possible choices for f is like trees and random forest, boosting, neural networks, and many more. Okay, we just include here a more complex function. Okay, so look at these two classes. We have apples and pears, and I want to decide where are the apples and where are the pears. Okay, so do you think logit and probit models can be used to classify apples and pears in the example below? Okay. What do you think? Think a minute about that. Okay. The fact is, what's the main difference between the two pictures? The pictures on your left and the pictures on your right. Okay. The difference is that, like the one on your left is like it's a linear separable. You can draw a line and separate the two classes, perfectly separate, like apples from pears. But the plots below, they are not linearly separable. You cannot draw just a single line and perfectly classify apples and pears. So these are more complicated problems, and these are problems that appears in classification and in large dimensions. Okay, so we need more complicated methods. Okay? So here, imagine that we want to fit a logit to this data. So you see here that we have two classes, 0 and 1, but they are not linearly separable. Okay. So if you fit a simple logit, you cannot do anything. But if you fit a logit of a square function, okay, like beta 2x squared plus beta 1x plus an alpha, then you can fit perfectly this data. So the idea is to have like this nonlinear argument to your probability function. Okay, so that's the idea. And now you can take all the tools that you have learned so far in this course and use it for them for classification. But instead of directly modeling a continuous random variable, what you're going to do is you're going to use these nonlinear models, these nonlinear tools, as an argument to this probability function G. And that's it, okay? As simple as that. So I'm going to give you an example about decision trees, and on Friday we are going to discuss about how to design a neural network to achieve our goal of modeling discrete dependent variables, okay? So what are classification trees or decision trees? The same as a regression tree, but with categorical dependent variables. So y take values on the discrete set between 0 and j, okay? And so the main difference is just the cost function that we are going to use to train the model. Okay? So basically, in a terminal node k of a tree, representing the region Rk with nk observations, we are going to write like the p hat kj will be the proportion of y's in the class j, okay? So this is the proportion of class j observations in region k, okay? So we are going to classify the observations in node k to class kj as the argument that maximizes this probability in j. So it's like the... So you have a region, you have the... Within that region, you compute the proportion of each class in that region, okay? So we classify an observation there as being of the class where we have the highest proportion, okay? And we have like possible criteria. We can like use as cost functions like the misclassification error, okay? And we can minimize the misclassification error. We can look at Gini index. We can minimize the deviance, okay, or the negative log likelihood, okay. So these are the possible criteria that we can use to train the model, okay. So remember that in a regular tree, what we do, we look into each leaf in each region and we compute the average. So the local model is the average of the observations, and we use like mean squared error to train the model. Here, the local model will be the maximum proportion, okay? And we are going to train the model by one of these four methods, okay? Minimizing one of these four methods, okay? That we can discuss more about them during our lecture on Friday, okay? So let's see how a tree can classify apples and pears here. We may start, of course we cannot do it with a single straight line, so this is not linearly separable. So we start putting a division here in the tree, and then we can come and put a second one here, and then we are going to take a third one here and a fourth one here, and bingo, a decision tree with this structure perfectly separate the apples from the pears, okay? Of course, real life is not that simple, it's much more complicated, okay? But that's an example on how these models can be very useful, okay? So on Friday, we are going to discuss much more about that. So this is our first class on classification, and next week we are going to go deeper into like these nonlinear classifiers, okay? But what I'm going to ask you is that think about how you are going to design a neural network model for classification. Okay, and we are going to discuss about this on Friday. So thank you. See you on our live session.